First of all, I want to thank the organizers for the opportunity to talk here this morning. Some of you might have expected Michael Schmucke, who was originally invited to give this talk. Unfortunately, Michael snapped a tendon in his knee and he couldn't make the transatlantic flight, so he asked me to stand in for him and give this presentation. Luckily, I was involved in the work, so it's going to be not too unnatural. What we wanted to do in this particular work, it reverberates with what was already said just now. We wanted to take a snapshot of what is actually there today and what we can do with it and how is it better or is it already better than conventional computing. So we were looking at that hardware is now available. Karl-Heinz Meyer showed those impressive pictures from the big machines in the Human Brain Project. It's also available in smaller form factors for embedded computing. And systems range here from dedicated hardware that is digital to mixed signal systems that have analog computing parts and digital parts for routing. Or we still have generic hardware that we can compare against, for example, the normal CPUs, GPUs systems. Now, what are next question we need to ask is what are the trade-offs? What is it actually we are looking for? And power was emphasized already. Another one I think is still we want to also be fast, exascale computing, for example. But the third one here, I think, is very important if we look at the uptake of this technology, is also how convenient and easy to use are these systems, and will they make mainstreams soon, or will they be so specialized that it's just for the experts, like us, so to speak, that will be only able to use these? So for this particular work, we asked the question, if you just take a standard benchmark task, and we grab a few systems to test, how will they do in the trade-off between these three elements? So we picked a couple of systems, and here we worked with Spinnaker. There's a picture here of the Spin 3 board on the top right. We have a very small system there, and we could later go to larger systems, but for the point of this comparison, we just took systems that were available at the time. We compared it against Spiky, some people might be familiar with it. So it's a mixed system of analog hardware, digital hardware, and runs at 10,000-fold speed up over real time, and also has a quite low footprint and low power. And then we compared it against something more typical or mainstream, if you want. So this is a GPU enhanced neural network framework. This is something we developed ourselves in Sussex. And we ran it on a standard gaming device. So this is a high-end gaming graphics card, the Titan Black with 2,880 cores. And as a task, we picked also something quite standard, and most of you will have seen this. So this is the handwritten data, handwritten digit set, where the question is to recognize these handwritten digits. Here's a nice way of visualizing that. We took that from this paper here. And it's hard to see, but here's a blow up. So you see in there the digits, and this shows approximately how the clustering structure of the similarity of digits are. This is a well-established task. Most people in machine learning have used it. So we know exactly what the performances of different algorithms and solutions are for this. It's fairly high dimensional, and that's important because we think, if anything, then neuromorphic solutions will be good in high dimensional tasks. And when we can scale the difficulty of the problem, we have up to 10 different classes, like the 10 digits. But we can also use subsets of it if that is too complex for these small systems we're testing here. And we have a good set of 60,000 training, 10,000 testing samples. So this is a kind of realistic type of machine learning problem. Okay, so we have a task, we have some hardware we want to test. Now the only thing that's missing, and maybe that's the most challenging part, is an algorithm that we're going to use that's neuromorphic and runs on all these three platforms. And so I'll give you just a bit of a flavor of what that's like, and it's a fairly simple system. So you also see later at the computational performance in recognizing the digits, it's not end of the bleeding edge of the performance on the MNIST data set. But at least it can be formulated on all these different hardware systems. And it works like this. So you first have to translate the problem somehow into something that the neuromorphic computing algorithm might understand. And under this, understand a neural network, basically. So something a neural network can understand. So the first step of that is encoding your input space into something that we can put in there. And for us, that means we need to kind of formulate some sort of rate type encoding of this, what's an image, before. And we did this with this virtual receptor approach. That's something that Michael has been spearheading for a while. And the idea is basically you have inputs, and they're here shown in the principal components, just abstractly as dots. And you want to encode those into a way where you have positive numbers that could be represented by a firing rate. And we do this by placing so-called virtual receptors that are these crosses in here. And then you encode every of the inputs just simply by its distance to these virtual receptors. So you see this red ring there, that might be one of the inputs you might encode. You look at the distance to the different receptors, and that defines you, through this simple formula, the activation of each of these virtual receptors. So you get a recoding in some positive numbers, in a vector of positive numbers of virtual reactor activation that gives you the encoding of that point. And it's a very general thing you can do with any kinds of inputs. Yeah, they live in some high-dimensional space, and then you can always make this kind of encoding. And then you can go ahead and pick your favorite network. Yeah, you might think in the future of doing deep learning or more advanced things. Here, this is a very simple type of model that also is it's Michael's idea. He has published this a couple of years ago. And this is a very simple network that does the following. You have these inputs here. These are these rates. And you encode them into spiking populations of neurons. They're called here projection neurons. This is bio-inspired by the olfactory system. And in the olfactory system, you have this antenna lobe, mushroom body pathway of recognition of odors. And that's where this inspiration comes from. The projection neurons, they are in the antenna lobe. So you have these projection neurons, and they just represent these firing rates as spikes. And then they inhibit each other slightly, which is basically a contrast enhancement type of algorithm, followed by supervised learning here. The dashed arrows are the plastic synapses and some associative neurons. So these will then represent the classes of your problem. In this case, there might be up to 10 of these, representing whether there was a 0, a 1, a 2, and so on present in the input. So they would fire and they inhibit each other strongly, so there's a winner-take-all kind of decision being made on this slightly refined representation here. It's a very simple system, and you see, I mean, the performance isn't huge, but this wasn't the goal here. Yeah? The goal here was to see, we put them onto these different available hardware systems and see, can we implement it? Does it work? And then how is it with the power and the convenience, and how is it with the speed? Now we had this idea, that's the basic model we wanted, and on the spiky chip where we implemented it first, we could pretty much implement it this way. But then when we went ahead and wanted to put it somewhere else, we had to do slight modifications. And here's the example of the GPU solution. We now have different underlying neurons simply because they were available. So there's also a choice, a trade-off between convenience and how much do you stick to the same thing in the benchmark. And then here we abstracted the inhibitory neurons out, so they inhibit each other directly. It's the individually stepped, it's just a way the GPUs work. Yeah? So you spawn kernels on a very frequent basis, which means you can spawn them per every time step. And we decided here to implement the plasticity outside the GPU. This was just a choice to match what we were doing with Spiky. This is something that can be discussed. And the same thing for the decision what class was recognized. And then again, we went to Spinnaker as the next thing, and we still had to modify slightly. So for example, it didn't seem to be practical in the end. We tried this first, but it didn't seem to be practical to do a full set of input spikes to represent our inputs. But it seemed to be more practical to put in the rates as inputs and then have a Poisson unit pool here to make us input spikes from that. That's something we had to learn, yeah, so that's one thing. The other one was that the learning now had to be on board because it wasn't practical to extract the spikes and like stop the Spinnaker in some way and extract spikes in the middle. That was just absolutely impossible to do, so we put it on the chip and used some STDP rule combined with a reinforcement signal in a sort of 3-factor rule to make the learning happen. So you see, it's details. I don't want to go through all the nitty-gritty of this, but we had to adjust details to make this model work on the different hardware. So there's no such thing as one neuromorphic algorithm, and you can just ship it out to different hardware systems and it will run. It is not like that. But as I will show you in a moment, we could achieve that they all perform on the same level, which gives us confidence that we did implement the same kind of algorithm in the end. There are also other differences. Yeah? There was the difference in how we implemented, how the connections are made, what kind of synapses and neurons are used and so on. But it has knock-on effects on how we do the actual operation of the system. So for example, on the spiky, we had to run it in a 1 second per stimulus simulated time. So we had to collect more spikes, so to speak, whereas on the Spinnaker, we could do this in 120 milliseconds simulated time. I should say, in practice, obviously, that means on spiky, it's much faster because it goes 10,000 times faster than real time, and this one goes in real time. But I wanted to point out that there's other things that you need to adjust to make this a valid comparison. Obviously, we could have run it here on the right-hand side with the Spinnaker longer too, but that would have been like a voluntary waste that we didn't want to put in because the speed measurement would be affected. So how we did all this was that we basically tried to do the best on each hardware and then compare. Yeah? So we tried to find out how long do we have to run every input to recognize it well on the Spinnaker. And that was only 120 milliseconds, whereas on the spiky was a second, and so on. So I hope it's clear that what kind of thing we were trying to do here, and I'll take you to the results now and show you this trade-off between accuracy, speed, power, and convenience. So the first thing, how accurate is the system? So here are some curves for the performance of the systems in real calls. So this is like digits recognized correctly. For different problems, here it's just comparing the digits 5 and 7, so a very simple problem, to the full system on the right here. Chance performance would be this dashed line down here. We did put it here too. And then these are the performances for different size of the classifier network. And if you do larger networks, you do a bit better. So you see you come from this 10 VR, 10 virtual receptors kind of representation to 200 VR system, and you get better and better. And then you see here Gen, that's the GPU-based system, versus Spinnaker versus spiky. The spiky was a bit size limited, so we just tested it on the 2 simpler systems here. And then for the larger stuff, we did the other 2 boards. Now, obviously, there's more available, and we can kind of push this further, but you, of course, can only benchmark at the time where you have the stuff available. So that's what was available at the time. And you see the total performance, that I should also point out, while it's consistent between the systems, it's not great in comparison to, like, you know, top of the line MNIST performances. They lie 99%. Yeah, so the best things that would be up here. This is just, you know, 90, 80%, depending where you are. So that isn't great, but it's a reflection of that simple model, so I wouldn't be worked up about it. What's important is that we got the same kind of performance in the different systems. For spiky, it's only realistic to compare this front one here. So we are encouraged that even though we did completely different implementations, we did get something that seemed to do the same thing. So for that, we're happy with that. Here's a bit more of a close-up between the Spinnaker and the Gen performance, and you see it really kind of clusters along the diagonal. So if you look at the performances against each other, they do the same kind of thing. Yeah, so this suggests to us that the limit of performance in recognizing digits is basically a limit on this kind of simple model that we did, rather than a limit on using neuromorphic hardware because it would be unreliable or something. It's not the point. Yeah, the point here is simply the model is a bit simple. Now let's come to the more interesting things. How do we now compare on speed and power? So here's the speed performance, and we try to kind of drill down a little bit into the different aspects of it. So in different colors here, I show for the four different systems. So this would be a simple CPU solution, GPU accelerated, Spinnaker, Spiky. We show the power for different tasks within the actual program system. And that was one of the interesting results here, really. So you see at the bottom always, that's kind of the time spent on actually executing spiking neural network computations on the hardware. So on the CPU, that scales linearly up, and you see it costs a lot once you get to larger systems. These are 3 sizes of systems each. On the GPU, on the other hand, it's just flat, basically, because you're not using all the cores, and on the Spinnaker, it's guaranteed real time, so that's flat on the bottom here. And the Spiky, again, we couldn't do the larger systems. And you see the comparison, yeah? So you see that you go through a point where for small systems, CPUs are just fine, to where they get really slow. And then between the Spinnaker and the GPU here, there's sort of a bit of a difference still. Obviously, if you went to much larger systems, then Spinnaker would eventually be faster. But then the first thing you might have noticed is that these little bars down there, they aren't actually that big compared to all this other stuff on top. Yeah? What's the other stuff on top? That's basically setting up the network on the device and transferring the input data in and getting the results out. Yeah? That's the kind of big chunk of stuff here. Yeah? And then there's some other tasks here in violet on top of different size. I should say in the Spiky here, the runtime's actually, this blue one's not the runtime. The runtime's invisible because it's so fast. Yeah? The actual runtime is almost nothing. And this blue is the setup time and transfer time. So we see in terms of speed, there's a lot of promise here, but it's not really fulfilled yet because either we're too daft to really use it efficiently, or because it really can't yet be used that efficiently in a practical applications, because you have to get system in, yeah, the algorithm in, and the data in, and the data out. And that is really, so you seem to be limiting at this point what you can do with it in terms of speed. Okay, that's speed. Now let's have a look at power consumption. Power consumption depends also a lot on the different phases of what you're doing. And that's here time resolved on these graphs. So here, this is the GPU system. Then you have the Spinnaker system here, and that's the Spiky. And the blue stuff here is GPU power. The gray stuff is the workstation where the GPU is in. And then here, similar, the bottom thin line here, that's kind of the baseline power used by the Spinnaker board, yeah, and then there is a workstation part in green that is about the support done while the Spinnaker was running things, and then the violet is the data preparation where the Spinnaker wasn't even actually involved. And here's a similar thing. Yeah, this is workstation again when you set up the system, and then you have the training run and the testing run for the Spiky system. And I think the first thing to mention, obviously, the neuromorphic systems are better with power consumption. The power is lower here and there than what the GPU is consuming there. So that's expected. Yeah? The GPUs are hungry devices. They're rated at about 300 watts for this particular GPU. So you will consume more power. Interestingly, it doesn't ever get to 300 watts. Yeah? So we're talking here about 40, 50 watts consumption. So they're not as bad as they seem on the peak power consumption that is mentioned. But you also see that the workstation support is taking a lot of power as well. And that's just the snapshot of what's happening now. Maybe in the future that's completely unsubstantial. But in terms of how we were benchmarking this, we wanted to see what's there now, how is it working now. And the truth is, right now we're wasting all this power on the workstation support for all these systems. And we're wasting all this time shuttling in data and getting it out, rather than having the benefits of the systems directly. That's the result that we found here. Now this is power consumption, and Obviously, they run different time lengths, so what's the total energy consumed for the computation? How do they compare on that page? And that's shown here. And you see the CPU is getting really bad if you go to large system because it runs long and needs a lot of power. Whereas here, the actual more neuromorphic systems start to look better. And yet again, the most power is taken by the most energy is used by the supporting PC. Now, I should say the method here was just integrating those diagrams I showed earlier of the power over time. Yeah? So this is reflecting the same results, but just reformatted for a better view. Okay, so that's power, which brings me to a quick summary of what we found here. So we found we can implement the same algorithm with a lot of work in the details, but we can implement them on the different available systems. That's possible, and they give the same performance in terms of their computational ability. In terms of the speed, the speed here was mainly determined by bandwidth. And one thing is that we can say, okay, that's just a temporary thing that we have to face now because these systems aren't fully embedded and developed yet. But I think it could also be a lesson to be learned what to pay attention to when developing them. It's not only about making the systems internally work well, it's also to make them work well in an environment for an application. So the bandwidth of how you get things on there and off is important and will stay important. The software interface, so that's the system that's always in the front that reformats your neuromorphic model onto something that's understood on the hardware. That is also a bottleneck. That takes a lot of time to set up the hardware. For example, on the Spinnaker system, when we tried this on a larger board, which we eventually did, we actually stopped doing it after a while because when we scaled it up, we hit like the 1 hour limit for setting up the system on the board, and the testing just became very, very tedious. So that's something that needs to be kept in mind. And then, of course, on the side of the algorithms, we didn't pay too much attention to this initially, but we can also set them up in different ways. And it would be important to set them up in ways that they don't communicate too much to begin with. So that is something to be looked at separately. So, for example, we could have chosen to do the plasticity always on chip rather than off chip. And that would have helped a lot. And the same for the input spike train generation. And finally, the energy consumption. To the date when we were doing this work, it was mainly the host workstation that was eating all the energy, and all the advantages of the systems that we had, which are running at much lower energy, were kind of eaten up by that kind of item. And that brings me to the end. Yeah? So I want to thank Alan, who is a postdoc with Michael and me, who has done all the legwork in this. Michael, of course. This was funded by the Human Brain Project, and the GPU-enhanced networks, they are funded by these folks in the UK. The whole work is published here if you want to see more details. So thank you very much.
Thomas? I'm not sure whether this is...
You can shout.
On? Yeah.
There you go.
So good to see you again. So very nice systematic work. It struck me that the results, all the burden in the uploading and the configuration that really dragged down the neuromorphic solutions. Of course, Spiky is Karl Heinz's 10-year-old platform, and so it'd be interesting to see what this looked like on HiCan. But for Spinnaker, it looked like very good performance, as equivalent performance in terms of the MNIST work, and really superior energy consumption once the uploading was done. And so it suggested that if you had a problem domain that was more of a streaming sensory processing, so where you upload the system, configure the system, you get that done, whether it takes 5 minutes or 5 hours, doesn't matter, but then you let the machine run with streaming sensory input for a long time, then really you'd have spectacular superiority in terms of energy consumption and at least equivalent performance. Is that what you would predict?
Yeah, I think that would be accurate. But one needs to keep in mind that unless you really run it continuously, there's no such thing as saving a state on Spinnaker and then reusing it again later, not as of yet. I think that would be something that would be interesting to look into. So you would have to do the re-upload. So if you had your streaming application, but you wanted to stop it and reconfigure some parameters or something in between, you would have to re-upload the whole process again. So that, and actually reroute at the moment everything again, which takes a long time.
Yeah, so just this local learning that Karl-Heinz was talking about, the learning and the homeostatic adjustment and other plasticity going on at a local level on the chip, then you're in the position to have streaming sensory input, which is after all what neural systems are for. That's what they evolved for. And then you really do show terrific advantages in terms of performance and power.
Yes, I believe so. I mean, it's a hopeful picture here. It may say we're not quite just there yet in terms of usability, but in the future I think you get these performance results on the power. So it is going to be much less power than the CPU, GPU kind of systems we're working on today. Yes, absolutely.
I'm actually a bit confused. In the case of the two neuromorphic chips, was the learning being done in loop, or was it done offline and then loaded onto the chip?
Was the running done?
The learning.
The learning.
Was it done in the loop, meaning the chip was being fed and then weight updates computed off chip and then loaded, or was it done off chip and then loaded?
Yeah, so the two systems differently. So for the spiky, it was done that it was run on the spiky, and then the weight update was done outside.
Off chip.
Off chip.
Okay.
And on the Spinnaker, it was done on chip, because the off chip wasn't even practical, and for the spiky, the on chip wasn't practical. So.
Okay, so for the spiky, it was in the loop.
So yes, it was done on the workstation. Yeah.
Okay, and for the case of Spinnaker, it was off chip or on chip completely.
On chip completely for the Spinnaker.
Okay.
Yeah.
So in this case, in the case of the speed, I'm a bit confused onto the configuration for the Spinnaker. Why it took so long? Because my understanding it would be that you configure the chip once, and then if the weight update is being done on the chip, then the only thing you're basically doing is applying the input vectors to the chip, and then just the chip will do everything from there on. Is that correct?
That's correct. That's correct. Yeah. I mean.
So why the excessive time taken by the configuration in this case?
Well, the excessive time taken for configuration is an upfront cost you have, where the neural network you want to simulate needs to be distributed on the different ARM cores on your Spinnaker system, and that's done in Python on the workstation. So there is a routing algorithm, and then later actually there's a C++ part as well. But the routing where it goes on your Spinnaker system is all done on the workstation. Then it's all uploaded. And then once it's running, you're right. Once it's running, there is no role of the workstation in there anymore, and it just does its thing. And then you have to grab off the results again, of course. Yeah. Okay. Thank you very much.